seen that exponential equations can be rewritten as logarithmic equations, and the base of the logarithm represents the base being raised to some power. And so the base can be any number, but it's very common for the base to be 10 because our numbering system is base 10. And so if we write something like log 100, and I didn't write a base here, it's understood that the base is 10. And so we can rewrite this as, let's say that y equals the log of 100. We can rewrite this as 10 to the y power equals 100. And you can probably guess that y must be equal to 2. So my point is that anytime you see a logarithm written without a base, the base is going to be 10. Now we also have another common base that we use very often. We'll talk about later chapters, later sections I should say, and that is the natural logarithm, and we abbreviate that Ln. And Ln is the same thing as saying the logarithm, where the base is e, and e is Euler's number. Euler's number is a constant, and it is equal to about 2.718, and there are more decimals in there, 2.71828. This goes on forever, it never repeats. It's very similar to pi as a constant, which is 3.14159, and that goes on forever and never repeats. And so these are two very common constants that we use all the time in mathematics. Your calculator probably has an E button on it, and more than likely your button probably says something like e to the x. And so I have a button on my calculator that says Ln. That stands for natural logarithm. I have a button on my calculator that just says log, which means log base 10. And so the Ln button means log base e, and where e is 2.71828, and that goes on forever without repeating. And if I hit my second button and then my Ln button, that gives me e to the x. And so it's common for e to be the base being raised to some power. Your calculator probably has something very similar to this on it. This is example 1. It says find log base 10 of 456, and also find log base 10 of 0.0596. And so we'll use our calculator to do this. The answer is not going to be a whole number or an integer even. It's going to be some decimal. And the book wants us to round to 4 significant figures. And so to do this, we want the log base 10. That's just the common logarithm. We call that the common logarithm. That's the button your calculator has on it. The log button means log base 10. So you hit the log button, you type in 456, and you press equals. And your calculator should say, I hope, 2.65, it says 896, which is going to round to 90. So I'm rounding to the 4th decimal place. It was 896. The 6 rounded the 9 up to a 10, which turned the 8 into a 9. For log base 10 of 0.0596, I'll hit the log button again, and I'll type 0.059 and press equals. And we get negative, and it's negative here because this number was less than 1, meaning that 10 is being raised to a negative number, meaning that it's in the denominator. So the answer is negative 1.2291. The next digit is a 4, so that rounds down. And so I can rewrite these in exponential form. This says that 10 to the 2.6590 power is equal to 456. So that's this logarithm rewritten in an exponential form. And this one says that 10 to the negative 1.2291 power is equal to 0.0596. And again, when the exponent is negative, this means 1 divided by 10 to the positive 1.2291 power. And that's the exact same thing, 0.0596. This is example 2. It says, given that log n is equal to 1.6845, find the value of n. And again, we did not write a base here, so it's understood that this base is 10. Now in the last example, they told us log of some number and wanted us to find what that equals. This time they're telling us that log of some number that we don't know equals a number we do know and find n. And so in order to solve for n, we need to first rewrite this as an exponential. We know that the base is 10. The exponent is the 1.6845, and this is going to be equal to n. And so we can find n on our calculator by taking 10 to this power. And so we'll type in 10, use the caret button for your power, or maybe you have a y to the x button, and you'll type in 1.6845, and you press equals, and you get 48.3615. 48.3615. And so that is the value of n. And we could rewrite this into the exponential form. I'll just write it out so that you can see. 10 to the 1.6845 power is equal to 48.3615. This is example 3. It says find the value of log 275 divided by log 5. And again, these are log base 10. They didn't write that there, but that's what it's understood to be. And so we use our calculator for this. We will take, we'll find the value of log 275, and we'll divide by the value of log 5. And so we'll take it one step at a time. The log of 275 is 2.4393, 2.4393, and the log of 5 is, my calculator is in engineering mode. Try that again. How about log 5? It is 0.6990 because I'm rounding. So we get 0.6990. And now we can divide. We'll take 2.4393 and we'll divide by 0.6990. And we get 3.490. How about 3.4897? So we get 3.4897. And that'll be the answer. And so I did this one step at a time, found those values, and then divided. My calculator will do all of this for me. I could just type in log 275, make sure I close the parentheses, and then divide by log 5, and again close the parentheses and press equals. And when I do it all at once, I do get a slightly different answer because I got some rounding error here. I should have kept more significant figures. If I wanted my answer to be 4 decimal places, I should have kept 5 decimal places in these and then divided and then rounded it to 4. So I do get a slightly different answer here. I get 3.4 and I get, let's see, almost out of ink, 3.4, 8, and this is going to round to 99. So you see I got a slightly different answer because I rounded my first answers here a little bit too soon. This is example 4. It says that pH is defined as the negative logarithm of the hydrogen atom concentration of a solution. And so it says if H plus is equal to 6.3 times 10 to the negative 5th, find the pH value. And so the pH will be equal to the negative logarithm of this number, 6.3 times 10 to the negative 5th. And we'll just use our calculator to do this. The pH will equal, and so we'll type into our calculator, we'll type in negative logarithm of 6.3 times 10 to the negative 5th power, and we get 4.201. 4.201. And so the pH is going to be 4.201. The book says to round to just 2 significant figures, or to 1 decimal place, which would be 4.2. This is example 5. It says that the intensity level of sound, which is beta, is defined as being equal to 10 times the logarithm of I over IO. IO is a constant. It's always 10 to the negative 16th power. That's watts per centimeter squared. And it says, what is the intensity level of sound with an intensity of 10 to the negative 11th? And so this is the value we're going to plug in for I. IO will be this constant value, and we will calculate beta. And so beta will be equal to 10 times the logarithm of I, which is 10 to the negative 11th, divided by IO, which is 10 to the negative 16th. And so again, we can use our calculator to do this. We will type in 10 times the logarithm of 10 to the negative 11th divided by 10 to the negative 16th. And we get 50. 50. And this number is measured in decibels. So this is the intensity of the sound measured in decibels. Like a jet engine is like 120 decibels, right? So that's loud enough to hurt your ears, is usually considered 120. 50 decibels is relatively not very loud. This is example 6. It says that the power gain or loss for an electrical circuit, an amplifier, or some other electrical device is defined as 10 times the logarithm of the output power divided by the input power. And so it says find the power gain, which would be in decibels, when the output power is 8 watts and the input power is 0.25 watts. So the power gain would be 10 times the logarithm of the output power, which is 8 watts, divided by the input power, which is 0.25 watts. And we'll just use our calculator here. So we'll take 10 times the logarithm of 8.0 watts divided by 0.25 watts, and we get 15.05. And the book says round to two significant figures, so we'll just have 15. So N is equal to 15 decibels. And that is the power gain measured in decibels.